For millennia, humanity has gazed upon the night sky, a boundless canvas of stars and galaxies, a cosmic tapestry woven from the fundamental laws of nature. Yet, beneath this visible majesty lies a universe shrouded in profound mystery, an intricate puzzle of unseen forces and unknown constituents. Modern science, our most powerful tool for unraveling the cosmos, constantly pushes the boundaries of our comprehension, revealing new layers of complexity and sparking deeper questions about reality itself. Our journey begins with the most pervasive enigma of the cosmos, the missing pieces. Despite our sophisticated instruments and theories, we understand only a tiny fraction of the universe's total composition. The vast majority of reality, nearly 95%, remains elusive, undetectable by direct means, hinting at profound unknown components that dictate the universe's structure and ultimate destiny. This unseen majority is primarily divided into two monumental secrets: dark matter and dark energy. Together, they represent the greatest challenge to our current understanding of physics and cosmology, forcing us to reevaluate our fundamental assumptions about matter, energy, gravity, and the very fabric of spacetime. Their existence is inferred not by direct observation, but by their undeniable gravitational influence. Let's first delve into dark matter. The concept emerged from observations of galaxy rotation curves in the 1930s, pioneered by astronomers like Fritz Zwicky. He noticed that galaxies in the Coma cluster moved too fast for the visible matter to gravitationally hold them together, leading him to postulate the existence of Dunkel Materie, or dark matter. Later, in the 1970s, Vera Rubin and Kent Ford's meticulous work on spiral galaxy rotation curves provided compelling, irrefutable evidence. They found that stars at the outer edges of galaxies orbit just as fast as those closer to the center, defying Newtonian gravity, which predicts a fall-off in speed at greater distances from the galactic core. This observed behavior could only be explained if galaxies were encased within a massive, invisible halo of matter, extending far beyond the visible starlight. This halo provides the extra gravitational glue necessary to hold these rapidly spinning galactic structures intact, preventing them from flying apart into the emptiness of space. Dark matter is not just in galactic halos. It's thought to permeate the entire cosmos, forming an invisible scaffold upon which the cosmic web of galaxies and galaxy clusters is built. Without its gravitational influence, the larger-scale structure of the universe as we know it simply wouldn't exist. So what exactly is dark matter? We know what it isn't. It's not ordinary or baryonic matter, the protons, neutrons, and electrons that make up everything we can see and interact with. It doesn't emit, absorb, or reflect light or any other form of electromagnetic radiation, making it utterly invisible to our telescopes. This means dark matter is fundamentally different from anything we've ever directly observed or produced in particle accelerators. Its strange properties suggest it exists beyond the standard model of particle physics, challenging our most successful theory describing the fundamental particles and forces of the universe. Scientists have proposed numerous candidates for dark matter, each one a hypothetical particle with unique properties. One leading contender is the weakly interacting massive particle, or WIMP. These particles would interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Direct detection experiments, like LUXePLIN and XENO-NNT, are buried deep underground to shield them from cosmic rays. They aim to observe the incredibly rare instance where a WIMP might collide with an atomic nucleus in their ultra-pure detector materials, causing a faint, detectable recoil. Another compelling candidate is the axion, a hypothetical ultralight particle proposed to solve a different problem in particle physics, known as the strong CP problem. If axions exist, They would form a cloud permeating the cosmos, and their detection would revolutionize our understanding of fundamental forces. Pioneering experiments like ADMX or the Axion Dark Matter E experiment are designed to detect axions by converting them into microwave photons within a strong magnetic field. These incredibly sensitive detectors push the boundaries of technological precision, seeking the faintest whisper of a cosmic secret. Besides WIMPs and axions, other exotic candidates include sterile neutrinos, which would not interact via the weak force, making them even more elusive than active neutrinos or even primordial black holes formed in the early universe, though current observations place tight constraints on their prevalence. The search for dark matter is a relentless quest, spanning continents and disciplines. From the depths of mines to the reaches of space, scientists employ every available tool, from highly sensitive particle detectors to gravitational lensing observations, hoping to catch the elusive signal of this invisible cosmic architect. The implications of discovering dark matter's true nature would be staggering. It would either unveil a completely new particle, extending the standard model, or perhaps even necessitate a modification of gravity itself on cosmic scales. Either outcome would fundamentally rewrite our physics textbooks. Beyond its particle identity, dark matter is intricately linked to the formation and evolution of structures in the universe. Simulations show that without it, gravity acting on ordinary matter alone couldn't have formed the galaxies and galaxy clusters we observe today within the age of the universe. The cosmic microwave background radiation, the faint echo of the Big Bang, also holds clues. Its subtle temperature fluctuations are consistent with a universe dominated by both dark matter and dark energy, reinforcing their central role in the universe's early moments and subsequent evolution. The precise distribution of dark matter helps explain anomalies like the Bullet cluster, where two galaxy clusters collided. Observations show the visible matter, largely gas, separated from the bulk of the mass, which continued onward, revealing that the dominant mass component does not interact electromagnetically. The hunt continues. Each non-detection from our current experiments narrows down the possibilities, pushing physicists towards new theories and more sophisticated detection techniques. The universe, it seems, is playing a very elaborate game of hide-and-seek with its most abundant component. Now let's turn our attention to the second major cosmic enigma, dark energy. In the late 1990s, observations of distant Type Ia supernovae revealed an astonishing truth. The expansion of the universe is not slowing down due to gravity, as expected, but is instead accelerating. This groundbreaking discovery challenged the prevailing cosmological models and ushered in a new era of cosmic mystery. Something, an unknown form of energy, must be exerting a repulsive gravitational force, pushing galaxies apart at ever-increasing speeds. This mysterious force was dubbed dark energy. Dark energy is believed to constitute approximately 68% of the universe's total energy density, making it the dominant component in the cosmos. Its properties are even more bizarre than dark matter's. It doesn't appear to dilute as the universe expands. The simplest explanation for dark energy is the cosmological constant, first introduced by Albert Einstein in his theory of general relativity. He later called it his biggest blunder when Hubble discovered the universe was expanding, but now it seems Einstein was inadvertently prescient. If dark energy truly is a cosmological constant, it represents the energy inherent in empty space itself, known as vacuum energy. But calculations based on quantum field theory predict a vacuum energy vastly greater than what is observed, by a staggering factor of 10 to the power of 120. This is one of physics' greatest challenges. This discrepancy between theoretical prediction and observational reality is known as the vacuum catastrophe or the cosmological constant problem. It suggests a profound flaw in our understanding of gravity, quantum mechanics, or perhaps both. It's a chasm in our knowledge. Alternative theories to the cosmological constant include quintessence, a dynamic, evolving energy field whose strength can change over time. Unlike vacuum energy, quintessence would vary across space and time, offering a more flexible explanation for the universe's acceleration. However, there's no direct observational evidence for quintessence yet, and the cosmological constant, with its fixed energy density, remains the best fit for current data. Future, more precise measurements will be crucial in distinguishing between these competing models. Dark energy's implications for the universe's ultimate fate are profound. If it continues to dominate, the universe might expand forever, leading to a big freeze or heat death, where galaxies drift apart, stars burn out, and all matter becomes infinitely diluted and cold. A more dramatic scenario, if dark energy increased in strength, could be the Big Rip. In this terrifying end, the accelerating expansion would grow so powerful it would overcome gravity, then other fundamental forces, eventually tearing apart galaxies, stars, planets, and even atoms themselves. Understanding dark energy is paramount to predicting the cosmic future. Larger-scale surveys like the Dark Energy Survey and the upcoming Vera C. Rubin Observatory are mapping billions of galaxies to precisely measure the expansion rate and its evolution, trying to discern the true nature of this mysterious force. These surveys utilize techniques like baryon acoustic oscillations, which are subtle imprints in the distribution of galaxies created by sound waves in the early universe, serving as cosmic rulers to measure the universe's expansion history with unprecedented accuracy. The synergy between dark matter and dark energy is critical. Dark matter provided the structural framework for galaxies to form, while dark energy dictates the universe's overall expansion trajectory. They are two sides of the cosmos's dominant, yet deeply unsettling, secret. The existence of these two unknown entities signifies that our current standard model of cosmology, while remarkably successful, is incomplete. It's like having a map where 95% of the terrain is marked terra incognita, awaiting brave explorers. Unlocking the secrets of dark matter and dark energy will undoubtedly require breakthroughs in both theoretical physics and experimental technology. It challenges us to think beyond our current paradigms and imagine entirely new forms of matter and energy. From the largest cosmic scales, we now dive into the smallest, the quantum realm. Here, another profound secret lies hidden: the inability to unify gravity with quantum mechanics. Despite their individual successes, general relativity and the Standard Model are fundamentally incompatible. General relativity describes gravity as the curvature of spacetime caused by mass and energy, working beautifully on cosmic scales. Quantum mechanics, conversely, describes the behavior of matter and energy at the subatomic level with stunning precision, using probabilities and discrete energy packets. The clash arises in extreme environments, such as within black holes or at the moment of the Big Bang, where both gravity and quantum effects become extremely significant. Our current physics breaks down, yielding nonsensical infinities and pointing to the need for a more fundamental theory. The quest for a theory of everything that unifies all fundamental forces, including gravity, with quantum mechanics, is arguably the most challenging and ambitious goal in modern physics. It seeks to describe the universe using a single, elegant framework. One of the leading contenders for this unified theory is string theory. It proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny, one-dimensional vibrating strings, unimaginably small, like cosmic rubber bands. The way these strings vibrate determines their properties, whether they manifest as an electron, a photon, or any other fundamental particle. It's like different notes played on a cosmic cello, each note corresponding to a different particle. A curious consequence of string theory is the necessity of extra spatial dimensions, beyond the three we perceive and time. These extra dimensions are thought to be curled up or compactified into incredibly tiny spaces, too small for us to detect directly. M-theory, a more overarching framework, suggests that different string theories are just different aspects of a single 11-dimensional reality. It posits point-like particles, strings, and higher-dimensional objects called branes as fundamental. Our entire universe, in this view, could be a three-dimensional brane floating within a higher-dimensional bulk. Interactions between these branes might even explain phenomena like the Big Bang, as collisions between branes. Loop quantum gravity, another major contender for quantum gravity, offers a different approach. It suggests that spacetime itself is not smooth and continuous, but rather quantized, woven from discrete loops or atoms of spacetime at the Planck scale. In this theory, space is fundamentally granular, not infinitely divisible. This could resolve the singularities predicted by general relativity, such as those at the center of black holes or the Big Bang, by preventing spacetime from collapsing to an infinitely small point. The challenges for theories of quantum gravity are immense. They operate at energy scales far beyond anything we can achieve in particle accelerators. The Planck scale, where these effects manifest, is so small that experiments are currently impossible. Nevertheless, indirect tests might become possible. For instance, tiny, subtle deviations in the speed of light from distant gamma-ray bursts, if spacetime truly has a granular structure, could offer faint clues. The implications of understanding quantum gravity are universe-shattering. It would illuminate the true nature of reality at its most fundamental level, explaining the very genesis of space and time, and perhaps even revealing if our universe is unique or part of a larger cosmic ensemble, a multiverse. The concept of the multiverse is perhaps the ultimate secret. It posits that our universe is not the only one, but just one of an infinite number of universes, perhaps vastly different from our own, existing in parallel or as part of a larger meta-universe. One leading inspiration for the multiverse arises from inflationary cosmology. The theory of cosmic inflation, which explains the universe's flatness, homogeneity, and the origin of structure, suggests that inflation may not have ended everywhere simultaneously. This eternal inflation scenario implies that new universes are constantly bubbling off from an inflating background, each potentially with different physical laws, fundamental constants, or even different numbers of dimensions. Another flavor of the multiverse comes from string theory's landscape. With its many extra dimensions, string theory allows for an incredibly vast number, perhaps 10 to the power of 500, of possible vacuum states, each corresponding to a different universe with unique physics. The quantum mechanical multiverse, or many worlds interpretation, suggests that every time a quantum measurement is made, the universe splits into multiple parallel universes, each representing a different outcome. All possibilities are realized in separate realities. This implies that somewhere, in an unfathomable number of parallel universes, every decision you've ever contemplated, every path not taken, has been actualized. It challenges our very notion of singular reality and personal experience. The mathematical multiverse hypothesis suggests that every consistent mathematical structure is a universe. In this view, our universe is just one specific mathematical structure among an infinite number of others, all equally real. The philosophical implications of a multiverse are immense. If there are infinite universes, does it lessen our own significance or amplify the incredible cosmic coincidence that our universe permits life? It adds another layer to the fine-tuning problem. A major challenge for the multiverse concept is its testability. How do we scientifically verify the existence of something we can, by definition, never observe or interact with. This pushes the boundaries of what constitutes empirical science. However, some speculative ideas for detecting multiverse echoes involve looking for gravitational imprints from collisions with other bubble universes in the cosmic microwave background, or searching for anomalies in physical constants. Even if direct detection remains impossible, the multiverse provides elegant solutions to certain cosmological puzzles, like the fine-tuning of fundamental constants that allow for life. Perhaps in an infinite ensemble, our universe is simply one of the few hospitable ones. The multiverse then shifts the question from "why is our universe so unique?" to "are we simply in a statistically probable corner of a much larger, diverse cosmic landscape?" It's a profound paradigm shift from uniqueness to cosmic plurality. From the incomprehensibly vast scale of multiverses to the equally incomprehensible dynamics within black holes, the universe's secrets continue to unfold. Black holes, cosmic behemoths, are central to our understanding of gravity's extremes. The black hole information paradox is one of the most perplexing puzzles in physics. Quantum mechanics demands that information can never be truly lost, yet general relativity suggests that anything falling into a black hole vanishes forever, erasing its history. Stephen Hawking's discovery of Hawking radiation, suggesting black holes slowly evaporate by emitting particles, exacerbates the paradox. If a black hole radiates away, what happens to the information of everything it consumed? It seems to disappear with the whole. Possible solutions to this paradox include the idea that information is somehow encoded on the event horizon itself, a concept related to the holographic principle, or perhaps tunnels, known as wormholes, allow information to escape to another region of spacetime. The holographic principle posits that the information describing a volume of space can be entirely encoded on its two-dimensional boundary. In essence, our three-dimensional universe could be a holographic projection of information stored on a distant boundary. If true, the holographic principle would profoundly alter our understanding of reality, suggesting that the universe is not truly three-dimensional but an elaborate projection. This is a radical reinterpretation of space and gravity. Wormholes, hypothetical tunnels through spacetime, offer another intriguing secret. These theoretical shortcuts could connect widely separated regions of the universe or even different points in time, revolutionizing space travel or enabling time travel. However, most traversable wormhole solutions require exotic matter, with negative energy density to keep them open, a type of matter currently unknown and possibly impossible. Their stability and existence remain highly speculative. If stable, traversable wormholes could exist, they raise profound questions about causality and paradoxes related to time travel. Imagine going back in time to alter events. What would happen to your present? The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that singularities, like those in black holes, are always hidden behind an event horizon, preventing naked singularities that could expose the breakdown of our physics. This hypothesis suggests a fundamental principle of cosmic order, preventing information from being lost or paradoxical time travel from being too easily achieved. It's the universe's way of maintaining its secrets. Beyond the physics of the very large and very small lies the pervasive question of life's origins and its place in the universe. Is Earth life unique or a common occurrence in the vast cosmic ocean? The search for extraterrestrial intelligence is one of humanity's deepest quests. The sheer number of stars and galaxies suggests a high probability of other life-bearing planets. The Kepler Space Telescope discoveries of thousands of exoplanets, many inhabitable zones, only strengthen this statistical argument. Yet the Fermi paradox asks, if life is so common and some civilizations could be billions of years older than ours. Where are all the aliens? Why haven't we detected any obvious signs of intelligent life? This silence is a profound cosmic secret. Possible resolutions to the Fermi paradox range from the Great Filter, which suggests some barrier prevents civilizations from reaching interstellar travel, to the idea that advanced civilizations deliberately hide or are too alien to recognize. The Great Filter could be behind us, meaning the jump from single-celled to complex life, or the emergence of intelligence, is extremely rare. Or it could be ahead, implying that technological civilizations inevitably destroy themselves or face cosmic catastrophes. The search for extraterrestrial intelligence, SETI, continues to scan the skies for radio signals, laser pulses, or other technosignatures that might indicate intelligent activity. Breakthrough Listen is a global initiative pushing the boundaries of this search. Detecting even a single, unambiguous alien signal would be the most transformative discovery in human history. It would force a reconsideration of our unique place, ignite scientific revolutions, and profoundly reshape our philosophies and beliefs. Beyond life, what about the nature of consciousness itself? Is it an emergent property of complex biological systems, or is it a fundamental aspect of the universe, intertwined with the very fabric of reality, a deeper cosmic secret? Some theories even speculate a link between consciousness and quantum mechanics, suggesting that conscious observation somehow influences quantum reality. While highly controversial, it hints at a profound, unexplored connection. The universe, in a sense, is observing itself through us. If consciousness is a fundamental, perhaps even universal, property, it opens up a dizzying array of possibilities for understanding reality that go far beyond our current scientific frameworks. The concept of cosmic evolution extends beyond individual organisms to entire civilizations and even planets. Are there cosmic principles that govern the rise and fall of intelligent life across the galaxy? Understanding the universe's ultimate fate, whether through the Big Freeze, Big Rip, or a potential Big Crunch, if expansion halts and reverses, is another profound secret. Our destiny is intimately tied to the universe's expansion. How much can we truly know? The limits of scientific knowledge present their own kind of secret. Are there fundamental constraints to what intelligence, even superintelligence, can ever comprehend about reality? For instance, is the speed of light a fundamental limit to information transfer, or does reality possess facets that transcend even this cosmic speed limit? These are deep epistemological questions, stretching beyond physics into philosophy. The future of scientific discovery holds the key to unlocking many of these secrets. Next-generation telescopes, like the James Webb Space Telescope and its successors, are providing unprecedented views into the early universe, peering back billions of years. Future particle accelerators, perhaps even spanning continents, called colliders of colliders, are envisioned to probe higher energy scales, potentially discovering new fundamental particles or dimensions hypothesized by quantum gravity theories. Quantum computing, while still in its infancy, might offer new ways to simulate complex quantum systems, potentially leading to breakthroughs in quantum gravity or unraveling the mysteries of entanglement, which hints at a deeper connectedness in reality. The search for gravitational waves, ripples in spacetime caused by cataclysmic cosmic events, is already revolutionizing astronomy. Future detectors, both terrestrial and space-based, promise new insights into black holes, neutron stars, and the Big Bang itself. The combination of observational astronomy, experimental particle physics, and theoretical innovation creates a powerful synergy, pushing the boundaries of human knowledge in unprecedented ways, steadily peeling back the layers of cosmic mystery. The universe's secrets are not static, they are dynamic, ever-unfolding frontiers. Each answer we find inevitably sparks more questions, driving the relentless pursuit of understanding that defines our species. Perhaps the next great secret is not a particle or a force, but a new understanding of information itself. The universe may fundamentally be an information processing system, with matter and energy just manifestations of cosmic data. This information-centric view, sometimes called it from bit, challenges our traditional notions of physical reality, proposing that information is the most fundamental building block, even more basic than energy or matter. The universe's ultimate secret may lie in deciphering the cosmic code, the underlying algorithms or principles that govern its existence and evolution. This leans into profound questions about the nature of reality and the very why of existence. Could the laws of physics themselves be emergent, rather than fundamental? Perhaps they arise from deeper principles or even from the statistical averages of simpler, more chaotic underlying interactions. The fine-tuning of cosmic parameters, where even slight variations could render the universe uninhabitable, continues to perplex. Is it a coincidence, evidence of a multiverse, or something even more profound? This fine-tuning problem leads to fundamental questions about anthropic principles. The idea that the universe must be compatible with intelligent life simply because we are here to observe it. Is it a tautology or a profound insight? Exploring the possibility of new forces beyond the standard four, strong, weak, electromagnetic, and gravitational, is another avenue for discovering the universe's next secret. Could there be a fifth force? Experimental anomalies in particle physics or cosmological observations could hint at such a force, interacting with dark matter or dark energy, or even mediating interactions between particles in ways we haven't yet envisioned. The nature of time itself remains a deep secret. Is it a fundamental dimension, an illusion, or an emergent phenomenon from more basic processes? The arrow of time and its relentless march forward is mysterious. Some theories suggest that time might not exist at a fundamental level, emerging only as a macroscopic average from a timeless quantum reality. Our perception of past, present, and future could be a cosmic illusion. The universe's extreme environments, the crushing gravity of black holes, the mind-bending conditions of the Big Bang, the energetic flares of quasars, act as natural laboratories for extreme physics, yet to be fully understood. The search for primordial gravitational waves, direct echoes of the universe's inflationary birth, offers a potential window into the very first moments of existence, revealing secrets about the conditions that set the stage for everything. Particle physicists push the boundaries of energy, hunting for supersymmetric particles, predicted by theories to balance out known particles, which could also be candidates for dark matter and help unify forces. String theory and M-theory continue to propose elegant, albeit abstract, solutions to the universe's deepest puzzles, offering a mathematical elegance that hints at a hidden underlying order. The convergence of astrophysics, particle physics, computer science, and even philosophy is essential. No single discipline holds all the answers. The universe's secrets demand a truly interdisciplinary approach. The human mind itself, with its capacity for abstract thought, creativity, and pattern recognition, is arguably the most remarkable instrument involved in this grand quest. Our curiosity is the fuel for discovery. We have learned that the universe is far stranger, more mysterious, and more wondrous than we could have ever imagined. Each solved riddle unveils a deeper layer of complexity, pushing the frontier of the unknown further out. From the dark particles that bind galaxies to the strange energy that accelerates them, from the fundamental fabric of spacetime to the potential for countless other universes, our cosmic exploration is just beginning to scratch the surface. The next secret could come from an unexpected discovery, a serendipitous observation, or a brilliant theoretical breakthrough that fundamentally reshapes our understanding of reality, just as quantum mechanics and relativity did before. It might be a direct detection of a dark matter particle, a definitive signature of a new dimension, or even a glimmer of life in an unexpected corner of our own galaxy, rewriting our cosmic story. The journey of scientific discovery is endless. The universe holds an inexhaustible supply of wonders, mysteries, and profound truths waiting to be uncovered by the persistent and ingenious curiosity of humanity. Imagine a future where we truly understand the nature of dark energy, harnessing its characteristics to manipulate spacetime, or traveling through stable wormholes to distant corners of the cosmos. Or conceive a world where quantum gravity is unified, allowing us to engineer spacetime at will, perhaps even creating miniature universes in laboratories. The implications are mind-bogglingly vast. The continuous pursuit of these answers defines our scientific spirit, pushing the boundaries of what is known and embracing the humbling reality that much remains shrouded in the unknown. What the universe's next secret will be, we cannot say, but we can be certain that it awaits us, hidden in plain sight, encoded in the subtle whispers of cosmic rays, the faint ripples of gravity, and the vast silence between the stars. It is a secret that will challenge our assumptions, expand our consciousness, and redefine our place in the grand cosmic scheme. It will be a stepping stone to even deeper, more profound mysteries. As we stand on the precipice of new discoveries, our instruments reaching further, our minds questioning deeper, we are poised to unlock insights that will once again transform our understanding of everything. The universe's next secret beckons, an invitation to continue this magnificent journey of exploration, forever expanding the horizons of human knowledge and our profound connection to the cosmos itself.